Hello students and welcome to the course Urban Rail Transit Tracks, Stations and Yards. In our last lesson, we talked about the important role of sleepers in the train tracks, especially wooden ones. Wooden sleepers are good because they are cheap and can bend, but they don't last long and can rot. This time, we'll look at the concrete and the steel sleepers and what makes them different when we build railway tracks. Because wooden sleepers were expensive to make, researchers looked at the other materials that could use for the tracks. In 1877, Joseph Monnier, a French gardener and inventor of the reinforced concrete, suggested using cement concrete to make sleepers for train tracks. He even made a design and got a patent for it, but it didn't work well. However, in 1890, Austria and Italy made the first concrete sleepers that actually worked. Other countries soon followed, trying out concrete sleepers on a big scale mainly because it was more economical. Concrete sleepers offer several benefits due to their unique properties. Their substantial weight, ranging from 200 to 300 kilograms, contributes to enhance the track strength and stability. These characteristics also grant them remarkable resistance against track buckling, which is particularly advantageous for maintaining the stability of CWR tracks. When paired with the elastic fastenings, concrete sleepers facilitate superior maintenance of the track gauge, cross-level, and alignment, while also excelling at retaining packing. Their flat-bottom design aligns perfectly with modern track maintenance and mechanical upkeep methods. Additionally, their poor electrical conductivity makes them suitable for the track circuit areas. These sleepers exhibit resistance to fire, insects, and corrosion, even in standard conditions. With a lifespan of around 40 to 50 years, concrete sleepers align rail and sleeper renewal schedules, yielding significant economic benefits. Their capacity for local mass production further enhances their feasibility. Moreover, the moldable nature of fresh concrete opens doors for innovative design and construction approaches. Meanwhile, concrete sleepers come with certain disadvantages. Firstly, their substantial weight makes handling and installing challenging, necessitating the use of mechanical methods that require significant initial investments. Secondly, in case of derailments, concrete sleepers tend to incur severe damage. Moreover, they can be recycled for scrap, which is downside. They are also not well suited for efficient packing. For proper maintenance, it is advisable to employ heavy on-track tempers. Moreover, there are several drawbacks to consider. Concrete sleepers are less elastic compared to wood, which might result in pumping on uneven tracks. They are susceptible to corrugation and can suffer from the effects of poor quality welds. Impacts such as derailments or loading or unloading can cause damage which cannot be repaired. The dynamic loads they experience and the stress from ballast can be up to 25% higher than other options. Lastly, concrete sleepers hold a negative residual value, adding to their drawbacks. Extensive research led to the creation of the modern railway track. This involved using CWR track. To support this new track, there was a need for improved sleepers, which are the supports under the rails. This led to the development of concrete sleepers, where many countries work hard to perfect the concrete sleepers for their tracks. In conjunction with reinforced concrete and pre-stressed concrete technologies, two types of concrete sleepers were developed. The first twin-block reinforced concrete sleeper comprising two trapezoidal reinforced concrete sections connected by a bar. The second is a monoblock pre-stressed concrete sleeper, which can be tensioned for added strength. A twin-block sleeper consists of two blocks of reinforced concrete connected by a coupling rod or pipe, which was developed in France. In ballasted track, the principal users are Algeria, Belgium, Brazil, Denmark, Greece, Netherlands, Portugal, Spain, and Tunisia. The twin block sleepers present notable advantages. They feature clear and defined bearing surface within the ballast bed, contributing to stability and support. Furthermore, their double set of surface areas significantly enhances their lateral resistance within the ballast bed. A monoblock sleeper is based on the shape of a beam and has roughly the same dimensions as a timber sleeper. This type of sleeper in new lines and renewal is widely used because it's considered to endure the higher and intensive loading better than the twin block sleeper. Monoblock sleepers offer several advantages. They come to a lower price point, making them cost-effective choice. Additionally, they're less prone to cracking, ensuring their durability. Moreover, these sleepers can also be pre-stressed, further enhancing their strength and performance. Concrete utilized in construction for centuries is resilient for compression but notably vulnerable to tensile forces, prone to breakage under significant pulling stresses. In reinforced concrete technique, concrete's weakness is pulling force effectively compensated by rebars, which are incorporated in order to reinforce a concrete against a pulling force. Thus, when significant pulling force is applied, the rebars are resisted, preventing breakage. However, it's unavoidable that the concrete will develop some cracks. That's why when monoblock reinforced concrete sleepers were initially introduced, it gradually exposed many shortcomings. These include a tendency to break easily when trim passed over them with force, as well as developing numerous cracks that could eventually lead to complete failure. They also lack the ability to handle repetitive stress, which result in a strong pulling force in the center of the sleeper. If these forces became too high and surpassed the sleeper's tensile strength, the reinforcing bars could shift or slip. To address these issues associated with concrete reinforced monoblock sleepers, railway engineers developed solutions using pre-tension and post-tension methods. These methods means pulling or stretching the sleepers in a controlled way before or after its pulling, making it stronger and last longer. In order to solve issues caused by reinforced concrete's susceptibility to pulling force and the inevitable development of cracks, the technique of pre-stressed concrete has emerged in civil engineering and construction. This method means putting pressures on the concrete using tendons before its use, which helps fix its weaknesses. There are two methods for applying pre-stress, the pre-tension method and the post-tension method. In the pre-tension method, PC steel's members are initially tensioned at a predetermined force and position. Concrete is then poured, allowed to harden, and subsequently the tension in the PC steel members is released, pre-stressing the concrete through the adhesion with the steel. Due to equipment-related constraints limiting manufacturing locations and transportation, the pre-tension method is primarily employed with a relatively small precast members manufactured in high volume. The monoblock pre-tensioned sleeper was developed in the United Kingdom. The sleeper is pre-stressed during its manufacturing process, which involves applying tension to the concrete before it put into surface. This pre-tension process enhances the sleeper's strength and performance, making it well suited for supporting railway tracks and withstanding the stresses of the train operation. The principal users are Africa, Australia, Canada, China, Hungary, Iraq, Japan, Norway, Poland, South Africa, Sweden, USA, and Russia. In the post-tension method, after the concrete has dried, we pull on the steel cables inside the tubes within the concrete. We hold on to this pulling force using anchorage fixed at the ends of the steel cables while pressing the concrete. Thus, the post-tension method is not limited to precast members, but rather can be easily used for structures with the proud at the work site. Additionally, a key feature of this method is that it allows for greater altitude, choosing the amount of tensile force to be applied. The monoblock post-tension sleepers was developed in Germany. After the concrete has been cast and hardened, steel cables and tendons are inserted into ducts within the sleeper and then tensioned. This process applies forces that compress the concrete, enhancing its strength and load-bearing capacity. Post-tension monoblock sleepers are known for their durability to withstand the demands of the railway operations, making them a valuable choice for supporting tracks and ensuring stable rail systems. Principal users are Austria, Finland, India, Italy, Greece, Mexico, and Turkey. Stress distribution of the sleeper has shown that in the central section, the developing stresses are very small. Therefore, less material can be safely used in this part of the sleeper. As a result, in the central part of the twin-block sleeper, the concrete was replaced by the connecting bar, which principally serves to maintain the track gauge. While in the monoblock sleeper, while the above solution cannot be applied, the cross-section at the central part of the sleeper was reduced. The use of concrete sleepers on the curved tracks is a controversial issue. In their metric gauge tracks, South Africa railways do not use concrete sleepers in the curves on the radius less than 300 meters. On the other hand, Canadian railways, which experience very extreme temperatures, from -40 degrees Celsius to +30 degrees Celsius, install concrete sleepers in all curves of radius less than 870 meters, including manual curves of radius less than 200 meters, with CWR and no gauge extension. The history of steel sleepers began as a steel industry developing in the end of the 19th century. This type of sleeper was an industrial product of the simple construction. It consists of a profile in the form of an inverted U, and their ends are forged to provide an anchoring in the ballast so as to ensure traverse track stability. Steel sleepers offer several advantages in rail track systems. They have a long lifespan, lasting up to 60 years, and eliminating the need for coach, screws, and saw plates are welded directly, reducing assembly complexities. They exhibit strong resistance to both longitudinal and transverse movement of the track, ensuring stability. The manufacturing process is simple and cost-effective due to low steel prices, eliminating the need for joint and impregnation. Moreover, they can be reconditioned, perform well under extreme conditions, and are suitable for challenging environments. However, there are also drawbacks associated with steel sleepers. They are susceptible to corrosion over time, leading to potential deterioration. The installation and maintenance costs for steel sleepers are higher. Following derailments, there can be gauge tightening issues, necessitating sleeper's replacement. The weld between the ribbed plate ceiling and the sleeper cover can be vulnerable. The low weight can result in poor track geometry. In the event of the derailments, steel sleepers can suffer significant damage. What's more, steel sleepers also pose insulation challenge with the signaling currents, making them unsuitable for track circuit areas. And that's the main reason of why steel sleepers are now only used on a very small scale. In summary, concrete and steel sleepers are valuable components of the rail track construction, each with its own set of advantages and disadvantages. The choice of the sleeper materials depends on factors like track requirements, budget, and the environment. In our next lesson, we'll explore further aspects of the railway sleepers. See you then.